Let's say they tell you to solve this recurrence relation using recursion tree. So recursion tree is a rooted tree. You start with the root. Instead of starting this way, we're going to do sideways. We're going to go this way. So this is the root. The label is going to be this right here, whatever it is, plug it in. It's T of n. This number here, this 1 tells you that this is only going to have one child. If it was a 2, you would have 2 children. If you saw a 3, it would be 3 children. But because we see nothing and we know there's a 1 invisibly there, it's going to be 1 child. What's that child going to be? This entire thing. It's going to be T of n minus 1. Why? Because what it's saying is that this problem we're going to solve by solving this sub-problem plus, 2 units of work. Or actually, I should say, the cost of solving this problem is going to be the cost of solving this sub-problem plus just 2 units of work. So this sub-problem, sub as in the problem is made smaller, we're making it smaller by subtracting from the problem. We're making it smaller by subtracting 1 each time. So what this means is you're going to take n and subtract 1, so you're ending up with T of n minus 1. And then from there, to get the next node, you again do minus 1. So from here to here, we did minus 1. So from here to here, we do, again, minus 1, because that's what we're saying. We're subtracting 1 every single time. So at that point, we would have subtracted 2 times from n. Like, we would subtract 2 from n. And then, so this would be T of n minus 2. And then if you go to another child, it would be T of n minus, well, at that point, you've subtracted from here 1 time, 3 times. You would have subtracted 3 times from n. So that would be even a smaller problem because you're literally decreasing n, which is like, the original size of the problem. And then you can keep going. So at some point, you're going to end up with one last node. And here's the thing. I like to label this with different colors. So each of these, we can call them a layer, or a level. So it's really just a column. It's just, this is a level, this is another level or another layer. And if you had 2 children, then you would have 2 children in this level. It's like 2 children in this column and so on. If you had 3 children, be 1, 2, 3, then in this green column, this green level, this green layer, you would have 1, 2, 3 children. That's the idea. But right now we only have 1 in each layer, in each column. So that's what we're dealing with so far. And I like to label these. I like to call them K. So this would be layer 0. K is equal to 1, layer 1. K is equal to 2, layer 2. K is equal to 3. And then at some point, we're going to have a last layer, and that's going to be K is equal to, well, you could say the kth layer, but we want to find out what that K is actually going to be, and we're going to find out in a second. But here's the idea. This here represents the time taken to solve this problem given, whatever is the size of the problem. And that's like this. The time taken to solve this problem is the time taken to solve this problem plus the time taken to solve this problem plus the time taken to solve this subproblem plus, however, we can't actually figure it out because we don't know what n is, but we could say, well, the worst it could be, the maximum time taken would be if it gets to the last layer, and it would also be plus whatever time it takes to solve that last problem in the last layer. So the idea is we kind of break it down just like we broke the whole problem down into pieces, into subproblems. We could also break down the time complexity, which is what we're doing. And we could just try to find the cost of just this layer and the cost of just this layer and so on. So all of the nodes in this layer, but there's only 1. So if that's the case, here is the formula. So the cost of a layer or of a level is equal to the number of nodes in that level times the cost of a single node in that level. So what this suggests is that the cost of a node in a level, so if you had 2 nodes in a level, their cost would be the same. That's what that suggests. So how do we do that? Well, for each of these levels, right, these columns, we want to be able to find the cost of that level. And then at the end of the day, we want to be able to sum up the cost. We want to sum up this from one level, K is equal to 0, to another, K is equal to question mark. We'll find out what that is. And that's going to literally give us the cost of the entire problem. But let's first start with trying to calculate this here. So let's do the number of nodes in the level. That's easy. How many nodes in this level, this column? You literally just see 1. Great. How many in this column? I just see 1. How many in this column? I just see 1. How many in this column? I just see 1. How many in this column? Well, we know it's going to be 1 because this here, again, this number is a 1. So we know that every subproblem is going to be have just 1 child. Okay. And then after that, we need to find out what's the cost of a single node in that level. So here's what's always given. This here is the cost of the first node. So we know that the cost is 2. So here we represent this as the cost of the non-recursive work for for just T of n, particularly T of n. But because it's constant, if it's a constant, no matter if it's subtraction or division, it's going to be the same for all subproblems, because what this is saying is that, okay, this problem is going to take as much time as this subproblem is going to take, plus 2 units of work constantly. Each time you have a subproblem, because it's constant, each time you have a subproblem, it's going to be 2 units of work. Each time you have a subproblem, 2 units of work. Another subproblem, 2 units of work. So the rule is if it's constant, it's just going to be the same cost for each subproblem. So in this case, the cost of this subproblem will also be 2. And the cost of this subproblem will also be 2. And the cost of this subproblem would also be 2. If it's something like n divided by 2 or something, n means that the cost, if it's just n, for example, n means that the cost of the non-recursive work is actually variable. It depends on what n is. And for example, in this case, if you're taking n and here you're taking n minus 1, now n is like smaller. So then the cost is also going to be, it's going to be changed. It's going to be variable to what n is now. That's a different n. And as in like whatever value is here, the size of the problem. And so that would be different. But we'll take 2 units of non-recursive work, and this will also take 2 units of non-recursive work. So together it'd be 4. And the way you do that is you say, okay, well, the cost of a single subproblem, again, they're the same, is just 2. And then you have 2 of these, so then this would be 2 times 2 is 4. So different ways to get it. All right, so that's the idea. We'll cover one where it's like n later, but this is where we're at. And then finally, once we get to the last layer, what's the cost of this node? Well, again, it's 2, because we just said if it's constant, it's going to be the cost of a single node for every single layer. Okay, great. So what this represents, notice that 1 times 2 is 2, 1 times 2 is 2, this is 2, and this is 2. What this is saying is that the cost of every single level is 2. That's how much work, that's how much units of like work you're incurring for every single level of the problem. So at the end of the day, we know we want to sum up the cost of every single level, and we know we represent level with a k. So we start from the first level, which we represent as k is equal to 0. So from k is equal to 0 to the last level, which we don't know what that is yet. And so that means we want to sum up all of this because we don't know how many, there are. At the end of the day, we just said, okay, they're literally all just 2. Like it's just 2 plus 2 plus 2. So in other words, the cost of every level, you can literally just replace it with 2. So 2, okay. So now we have this. Now the thing that's left to do is find what's the last level. Okay, here's what you do. So to find what the last level is, you ask yourself, how many times do you have to, or do I have to? Because you're asking yourself. And then whatever operation is here, if it's subtraction, you put subtraction or subtract. If it's division, you put division or divide. So in this case, it's subtraction. So how many times I have to subtract, and then by whatever number you're subtracting from, that constant 1, from where you're starting. This variable here is n. That's where you're starting. That's the size of your problem. And each time you're reducing your problem by subtracting 1 each time, right? And so you're asking yourself, okay, how many times do I have to subtract 1 in order for me to get to this node here? Well, then you think about, what does this node represent actually? We know that this is the last layer, right? Something we know about the last layer of like a recursion tree is that the nodes there are base cases, because we know that recursion stops when it reaches a base case. So then you ask yourself, okay, what would be the base case here? You don't really have to have a context really of the problem. You just think, okay, well, I'm starting here at n, and each time I'm subtracting 1 from n each time. And so then at this point I've subtracted 1, and then at this point I've subtracted 2, and at this point I've subtracted 3. And so if I keep subtracting 1, at some point I'm going to end up subtracting n, right? I'm going to end up literally subtracting n. And so once I get to n minus n, that's going to give me 0, and that would be a base case, because that would be, it's like usually either 0 or 1 or 2, whatever, depending on your problem. But in this case, your problem would be done because you literally you basically reduced the problem to where like it's just not even a problem anymore. It's like solved. It's like t of 0 is something you could solve. Like n, like the size of the problem just like you reduced it so much. So t of 0 would be the base case. And so the goal is, how many times do you have to subtract 1 in order to go from to 0? Well, you would have to subtract 1 times. So you would literally have to subtract. So to get 0, you would have to subtract n times. And the idea is, if you have 5, and I'm asking you how many times do I have to subtract 1 in order to get to 0, well, it would be 5 times. Like, I would literally have to subtract 1 5 times, so it's just 5 minus 5 is 0. If I had 6, how many times do I have to subtract 1 to get to 0? Well, 1 6 times, so 6 minus 6 is 0. That's the idea. So if I have n, how many times do I have to subtract 1 to get to 0? Like, to literally get rid of n? Well, I just get rid of n, like, by subtracting n. So that's the idea here. So this here, this answer is your last layer. It's going to be, well, where's my highlighter? What color do I use? Blue? This here is going to be n. That's what we found. So now it's just a series thing. Okay, so then from there, this is the interesting part. You have to know your series. At some point, I really am working on a cheat sheet because, I mean, in Calc 2, we literally just learned, hey, does this series converge or diverge? Like, we didn't focus on, like, rules. It was just like, does it converge? Does it diverge? Like, that's it. Like, I don't know. They just assume. And let me not even get started. Okay, so hopefully I get a cheat sheet out. But here's the thing. There's a formula that says if you're summing up from one number and you're summing up a constant, basically, you're literally saying, hey, I'm summing up a constant c literally n times. So it's c plus c, however many n times, because it's like 1 to n, it's just n times. So the formula says, okay, just take c. If you're summing it up n times, then you're literally just going to have c n times. So the formula is e times n. And so the problem is I want to use that here, but this has a 0. So I have to rewrite it such that there is a 1 here, and then I can just leave everything by itself. And then what this is saying is, to put it into perspective, this here, from 1 to n, from layer 1 to layer n, is all this, right? All of this stuff. Adding all of this, right? But I have to make it equivalent. I have to basically, what this was from layer 0 to layer n. That was the entire thing, right? So this entire thing. But I got rid of that. So I have to basically add it back. And we know that this represents the cost of a level. So the cost of level 0, which is what I didn't include here, is literally 2. And you can think about it, k equals 0 means, okay, you want to plug in 0 for k, but there is no k. Like, no matter what, the at whatever level is going to be 2. It's a constant. Like, there's no k that you can plug in there. So at k is equal to 0, at level 0, the cost is 2. It's just constant. So you could just add that plus 2. And so then this part is that. So now you have the green part plus the blue part makes the whole thing. But then that allows you to use this formula because now you got the 1 here. So the formula says, okay, just take 2, multiply it by n, literally just this little shape here. This here becomes 2 times n because you're literally saying, hey, I'm adding up 2 n times. So then literally just write 2 n times, 2 times n. And then drop down the plus 2. And then you get that your t of n, the time taken to solve this problem, is equal to 2n plus 2. And to find your O, you get rid of any constants. You focus on the dominating term. This is literally the only dominating term. And by term, I mean like the variable. And you get rid of any coefficients besides exponents. If you had an exponent, you wouldn't get rid of any exponent. You would just get rid of any numbers like a coefficients attached to it. So then because this is what's left, that's it. And so the answer is O of n. That's it for this video. I'll see you in the next.